Here we're going to learn about inverse functions in three parts. First, we're going to talk about the graph of inverse functions. And then we're going to verify if two functions are inverses of each other. And three, if you're given one function, you have to find the inverse of that function algebraically. So let's first start with the graph. A function has an inverse if the graph is a one-to-one function. What does that mean? It has to pass the horizontal and vertical line test. So what that also means to pass the horizontal and vertical line test is the function doesn't have any repeated x's or y values. Let's make sure you understand what a one-to-one function is. If I was to give you a picture of a parabola, and we go ahead and we do the horizontal, well, let's back up. We're going to do first the vertical line test. So you just draw random vertical lines, and if it intersects in just one spot, then you do not have any repeated x values. So vertical line test, we're good here. Now we're going to do the horizontal line test. Draw a bunch of random lines. If it intersects more than once, like here, almost in all of them, then that means it has repeated y values. Therefore, it fails the horizontal line test. So the quadratic function will not have an inverse because it fails the horizontal line test. Okay, let's look at another function. Here I'm going to draw square root function. So this is f of x equals the square root of x. So again, a one-to-one function has to pass the horizontal and vertical asymptote. Vertical and horizontal line test. So vertical line test, it intersects in just one point. Horizontal line test, it intersects approximately at 1 point. So the f of x equals square root of x has an inverse. Okay, now we're going to compare inverses. To verify inverses, you have to use composition of functions. So you're going to do the composition of functions for both f of g of x and g of f of x. If f of g of x equals x and g of f of x equals x, then f of x and g of x are inverses of each other. That's it. You just have to do the composition of both f of g of x and g of f of x. And they both have to equal x, nothing else. So let's practice. Okay, so here's our example. Verify if f of x equals 3x minus 2 and g of x equals x plus 2 over 3 are inverses of each other. So we have to test both. We have to test f of g of x, and we have to test g of f of x. So let's get started. For f of g of x, we are plugging g, x plus 2 over 3, into f, which is 3x minus 2. So to continue, we have 3 times our x is x plus 2 over 3, close parentheses, the minus 2. 3 times that quantity, the 3's cancel. So what we're left with is x plus 2 minus 2 the 2's cancel, and we get x. So f of g of x equals x. Now let's do g of f of x. We're plugging f of x, which is 3x minus 2, into g of x, x plus 2 over 3. So wherever there's an x, we're going to substitute 3x up minus 2. Okay, so here we simplify the numerator, the 2's cancel, and we have 3x over 3. Then the 3's cancel, and we are left with x. So g of f of x is also x. Because both of them equal x, we can now conclude that f of x is an inverse of g of x. Or you can reverse it. It means the same thing. And you can say g of x is an inverse of f of x. Okay, now we're going to find an inverse. And here our function is x squared plus 1, but only when x is less than or equal to 0. Now, I'm probably wondering, why are they restricting the domain with x is less than or equal to 0? The reason is, if we were to graph x squared plus 1, that's a parabola shifting up 1. And here, we would not have a function. We would not have an inverse because it would fail the horizontal line test. But if we take only the part where x is less than or equal to 0, well, x is 0 here, the graph goes in this direction where it's less than, so we can get rid of all of that. Now this part of the graph does have an inverse because it passes both the vertical and horizontal line test. Okay, so here's how you would find the inverse. Remember, we have f of x equals x squared plus 1. What we need to do is switch our x's and y's. F of x means y. So what we do is we replace x with y and with y's with x, like this. The y becomes an x equals y squared plus 1. Now we solve for y. So in order to solve for y, we're going to bring, we'll bring the y over. So we have negative y squared, and we're going to bring the x over, so 1 minus x. Divide everything with a negative 1, which flips it to y squared equals x minus 1. Now, to get y by itself, we have to square root both sides. Whenever you add a square root, you have to add a plus minus. So we have y equals plus minus the square root of x minus 1. Now, if I was to graph this, I would end up having a shift to the right. I would have this. And that there would fail the horizontal, the vertical line test here, and it would not have a function. But because it says x has to be less than or equal to 0, we would take the negative here. So our final answer would be y equals negative square root of x minus 1. So what does that get rid of in our graph? This part. And as you see, our graph now is a 1-to-1. So another graphical characteristic of inverses is that if they're inverses, they reflect about the origin, which is y equals x. And if you fold along this line, f of x would be on top of our new function, which is in blue. So our final answer here, what is our new inverse? Our new inverse is y equals negative square root of x minus 1. You could also write that as the inverse of f of x is negative square root of x minus 1. Okay, so here's our second problem. We're just going to focus on this algebraically. Find the inverse of f of x equals x minus 2 over x plus 2, where x cannot equal negative 2. If x was negative 2, we would have a 0 in that denominator, which would make the function undefined. So that's why they state x cannot equal negative 2. So we are going to we have f of x is y, x minus 2 over x plus 2. We are going to switch our x's and y's. So it changes to x equals y minus 2 over y plus 2. And now you solve for y. This is all algebra moving forward here. To solve for y, I'm going to multiply both sides with y plus 2 to get rid of the fraction. These cancel. And on the left side, we will distribute the x and have xy plus 2x equals y minus 2. Now you want to keep in mind that we want to isolate our y, but we have two y's. So what we want to do is bring all the y's on one side. So xy minus y equals negative 2 minus 2x. Now these two y's, to make them into one, I'm going to factor out a y. And I'm left with x minus 1 equals negative 2 minus 2x. So from this step, which is almost our last step, to isolate the y, we have to divide both sides with x minus 1. So these would cancel, and we would have y equals negative 2 minus 2x over x minus 1. So therefore, our inverse of f of x is negative 2 minus 2x over x minus 1. And our domain, x cannot equal 1. And there is our inverse. So just a quick recap. A graph will have an inverse if it's a one-to-one function. And what I'm going to add to this is also inverses reflect about the origin, which is y equals x. Second, when you verify functions are inverses of each other, you have to do the composition of both of them, and they have to equal x. If they both equal x, then they are inverses of each other. And to find the inverse, what you need to do is switch your x and y and solve for y, and that's where all the algebra happens, and you'll get your inverse.